students, now we have come to the fourth experiment in physics within the section measuring instruments. First we saw vernier caliper, then we saw micrometer screw gauge. The third one we have seen how to use a spherometer, and this time we are going to see a travelling microscope, right. So, this is nothing complicated, it is also a simple microscope and getting the measurements is very easy. Only thing is there are several parts of this instrument. So, what we do with each part, what is the name of each part, how do we handle each part, that has to be known in detail because they ask that in exams. And obviously, if we do not know the meaning and the usefulness of each part, then you can't use this instrument properly. So, take some extra effort to remember each part of this travelling microscope. For that, rather than just memorizing it, if you observe how we are doing this experiment, if you observe it couple of times, then you will understand it better. Clear? Right. You can see here, this is what we call travelling microscope. Let me explain it to you. This is what the microscope part is. This is what microscope. It has two lenses. The eyepiece is here and the object piece is here. Objective we say. Right. So, this is just a microscope. How it is going to be used? Imagine you have a rubber tube. Rubber tube of which you want to measure the diameters, internal, external diameters you want to measure. You can't use vernier caliper for a rubber tube because rubber tube is not, it doesn't stay on a fixed shape. Let's say you put the internal jaws and try to pull it, then it will change its shape. It will get deformed. Then the correct internal diameter, external diameter, you will not be able to measure it. Say you put the external jaws of the vernier and keep closing the gap, then the rubber tube also will get deformed. It wouldn't stay in the circular shape. Therefore, without touching the rubber tube, we have to take the diameter measurements. How we do that? If you are using this, look at this. If you are using this, how we do that? Right. Let's say this is your rubber tube. So, what you do, fix it on a stand such that it remains horizontal, right. Then, let us say you want to measure the internal diameter. To measure the internal diameter, within this microscope you can rotate it, you can observe in any direction, you can rotate it if you want, you can observe vertically, you can bring it horizontal, you can look upwards, you can measure in any direction. So, make it horizontal, right, and first focus on this rubber tube's end, see whether you are able to see this clearly. Then you adjust your crosswire, there will be a crosswire, bring the crosswire to this position, that means in this diameter to one side of it. Then we can move the travelling microscope. Not with the entire thing, there is a railing here. See, we have a railing. So, on the railing, we are going to slowly move it and move the crosswire to the other side. Get the reading 1 here, get the reading 2 here. The difference between reading 1 and reading 2 is going to be the diameter. Understand? So, we simply have a microscope here which has the facility or which gives us the facility to move it. And you can measure by how much it has moved. That is why we call it travelling microscope, right. So, this is the microscope, and if you look at this railing, this part is all about moving it vertically. Sometimes you want to get vertical measurements. Look at this, you can get the reading here, reading here. So, you have to move it vertically, right. First get the reading here, move it up, get the next reading, the difference is going to be again diameter. Right. So, this part, like this entire parts is to give you the facility to move the microscope up and down vertically. And this one, the railing here, is to move it horizontally. That's why we call it travelling microscope. Understood? Right. With that background, now let's look at the parts here. Look at it clearly. See, we have two screws here. Let's start from that. First step is, before you use the travelling microscope, you have to make sure the base of the travelling microscope is kept horizontally. Right, not angled, not parallel to the table. If you say it has to be kept parallel to the table, wrong, because table may not be horizontal. Right, we have to keep it horizontally. How do we ensure horizontal? Now you can see there is a bubble level here. See what we see here. Can you see a small part here? That is a bubble level, spirit bubble level. Right. So in that you can see if the bubble remains in the middle or not. If the bubble remains in the middle, then it's leveled. It's horizontal. If bubble goes to a side, it is not leveled. Then if it goes to a side, if the bubble goes to a side and you understand it is not leveled, then what we do? We change these screws. We can adjust these screws and bring the bubble to the middle. That's why we call these two as leveling screws. Leveling screws. Using those two screws only, we are going to level the microscope, travelling microscope. And this is what the bubble level is. Using that only you ensure whether the travelling microscope is leveled or not. Bubble level. Right. Then let's go up here. See, can you see this one? It's a clamp type screw. It's a clamp type. It's a clamp basically. If you loosen this clamp, then the microscope will be free to move up and down. So if you move it and leave your hand, it will fall down. It will get damaged. It won't easily fall down that faster, but there's a chance it can fall down. So what you must do, you loosen this, hold on this clamp and carefully you can take it up or down. Approximately 15 centimeters you will be able to take up and down. Clear? Right. So how we call that? Screw to adjust it vertically, to move the microscope vertically. The clamp type screw or clamp or screw, whatever you can say, to move the microscope vertically. But sometimes what will happen, imagine if you are using a capillary tube. You want to get the diameter of the capillary tube. Capillary tube also you can't use with the, you can't find the diameter with the vernier because it's very narrow. Internal diameter is very small. So you can't use a vernier caliper for that. Again, this is required. You fix the capillary tube in front of the microscope, focus the microscope in one side and then move it to the other side, get the difference. So by how much you have to move up and down, it's a very small amount because capillary tube will have part of millimeters as its diameter. So if you just adjust it with your hand, it might go by a bigger extent. So if you want to fine tune the vertical position of microscope, then what we do, you tighten this clamp and then you can use this screw for that. Screw for fine adjustment vertically. Screw for vertical fine adjustment, we say. Fine adjustment, like parts of millimeter, little by little if you want to move it vertically, that's what we use. So you have two screws to adjust vertically. Same thing is there horizontally also. Can you see? There is a like silver color screw here. Can you see? That is the one you have to loosen to move it horizontally by a bigger extent in few millimeters, few centimeters if you want to move manually. Right? So we call it the horizontal movement screw or screw for horizontal adjustment or screw for horizontal movement, whatever. And again you have another screw here. This is for screw for fine movement horizontally. Screw for fine horizontal movement we say. That means once you have moved it, let's say okay, this is how the circle is. You have brought it to this point, but you want to bring it here. But when you move it by hand, it goes by a bigger extent. Then what you do, remember this point. Tighten this screw, the screw for large movement, tighten that screw and then rotate this screw, you can see it moving. If you don't tighten this, then this screw wouldn't work. However you rotate that, you won't see a movement. Once even they asked this in the exam. When you rotated the fine horizontal movement screw, the student observed that the microscope is not moving. What could be the reason? Many students wrote the equipment is corroded. Equipment is broken. No, it's not broken, it's not corroded. The reason is you have not tightened this screw. Similar problem is there for vertical adjustment also. If you don't tighten the screw, with this screw you can't adjust it. But the thing is, nobody will leave it without tightening it, because if you leave it loosened, it will fall. It wouldn't stay at a point. So, vertical large movement screw, nobody will leave it loose. But horizontal, even if you don't tighten it, if you leave it loosened, nothing will happen. Nothing will happen. Therefore, chances are there, after adjusting it manually, you might forget to tighten this. If you forget to tighten this screw will not work. You tighten this properly, then only this screw will help you. Right? So, that's the vertical adjustment screws, horizontal adjustment screws. There are two, one for large movements, one for fine movements. Then, to see like, okay, from this point to this point, if it has moved, we need to measure how much it has moved, right? We have scale for that. This is the main scale and there is a vernier scale. See, look at this small one, that's a vernier scale. So, you can get up to 0.1 millimeter accuracy usually, you can take it. Similarly, vertically also, on this copper color plate, right? You may not be able to see that clearly here. When I show you the instrument, you can see that there is a main scale. See, this is the main scale and this is the vernier scale. Vertical vernier scale, vertical main scale, to get the measurements vertically. And then coming to the microscope part of it, you have an eyepiece. There is a lens basically, lens. Right? When you look through that lens, you will be able to see a crosswire. You may have to adjust that up front and back to see the crosswire clearly. Right? Depending on your eye power, you have to set your eyepiece so that you see the crosswire clearly. This is what you call objective lens. Objective lens. And this knob or this screw is used to focus, right? Say you kept a object in this, either you can move the microscope forward and backward manually, like you can take it, move it up and front and back manually and get a focus, but this will be a fine focus. You can use this knob to focus and get the clear image of the object, right? This is all the parts of a travelling microscope are. When I take the instrument, again I will explain all these parts, observe it carefully, right? So, if you know the parts, then it is very easy. Use of the travelling microscope, finding the internal diameter of capillary tube. You need to understand why we need travelling microscope for this. Why not a vernier? Internal diameter of a capillary tube, you can't put the vernier's jaws into the capillary tube, it is very small. Therefore, vernier is useless. That is why we need this one. Finding the internal diameter of a rubber tube. Rubber tube, why can't we use vernier? If it is a PVC tube, we can use vernier because PVC tube doesn't get deformed. But rubber tube can get deformed. When you give pressure, when you pull it, push it, it gets deformed. It gets into different shapes. That's why vernier won't be useful. Vernier caliper is not useful. We are using travelling microscope. Same external diameter also. And also remember, sometimes we may have situations where, let's say there is an air bubble within a fish tank. From outside you want to measure the diameter of it. So, you can't take the air bubble out and measure it. You can't go touch the air bubble and measure it. So, obviously you have to be in distance and measure it, right? So, in such cases also the travelling microscope is going to be useful because you can't touch or take the object. Travelling microscope, capillary tube, rubber tube and stand. Stand is to fix these tubes. Right? That's all the materials and apparatus required. In an instrument with vernier scales, if end divisions of the main scale coincides with capital N divisions of the vernier scale, then least count is 1 minus n over n into length of a smallest divisions of the main scale. This we studied when I did vernier caliper itself. We studied if there is a vernier scale, main scale, how to find one division of vernier, how to find the least count, all that we have seen. There is no concept of zero error here, because when you use microscope, travelling microscope, it's always going to be one reading, another reading difference. So you need to see first where it was, then where it has moved to, get the difference is what you call whatever the measurement that you want to take. Therefore, there is no concept of zero error here. Spherometer and travelling microscope, we don't talk about zero error, because we don't start from zero, right? See, for example, when you are measuring the diameter, first you keep it here, get reading 1. Then move it here, reading 2. Reading 1 to reading 2 difference is going to be the diameter of this capillary tube. So, since we are getting the measurement difference from one reading to the other, there is no concept of zero error here, right? Method. First, determine the least count of the travelling microscope and note it down. Using a spirit level and adjusting the leveling legs, level the microscope. So, here you have this leveling problem, because other instrument we didn't have a leveling thing. Maybe spherometer we had to keep it on a plane surface. Others we never had this leveling issue. Here it is important. Unless you keep the base horizontal, then the measurements you are not going to get correctly, right? So, make sure it's kept horizontally. Fix the capillary tube coaxially with the microscope part of the instrument on a stand and focus the face of the capillary tube by the microscope. Coaxially means, okay, let's say this is your microscope. So, bring it horizontal. In the same axis, you have to keep the capillary tube like this. That's why they say coaxially. Then only you get the readings correctly. See, if you keep the microscope like this and the capillary tube like this, you might not get the correct readings. You have to be keeping it coaxially. That means the axis of microscope and the axis of capillary tube must be the same straight line. Same straight line. Move the microscope horizontally until the cross wires of the microscope get adjusted as shown in the figure, and using the horizontal scale observe reading x1, x2. Figure is this. See, x1, x2. I already explained that. Similarly, you remember, like when you are doing this, you are getting the diameter here. Then we get the diameter on the other direction also, because it might not be a uniform circle. It may not be a perfect circle. So, the diameters can slightly vary, angle to angle. So, we take two perpendicular diameters and get the average. Next, move the microscope vertically until its cross wires get adjusted as shown in the figure, and using the vertical scale observe readings y1 and y2. Clear? So, that's all. Like the average of these two will be the diameter. Careful. Now when we use let's say the vernier caliper to get the external diameter, what we do, we take it at multiple places and we get the average. Here we can't take it at multiple places because only the front side you can take it. If it is a short one, maybe front side and back side you can take it. You can't take it in the middle. Then you have to break it and take it. So, that we don't do it. We don't break the capillary tubes unnecessarily. So, you just take it only on the front side, but in two directions, 90-degree angle, you take it separately. When measuring the external diameter of the rubber tube, arrange it so that cross wires are in contact with its external surface. See, like this is for internal, external has to be like this. Then the difference between these two will be the external diameter. Similarly here, like this, arrange it vertically on the external walls of the rubber tube and get the readings. Clear? Do you understand? Right. So, that's very simple. Apart from, there are a lot of parts in this instrument. The usage and the calculation is very simple. Even when it comes in the exam, they ask a lot of questions about the parts. What is that part? What is this part? Name the parts. What's the function of the part? Likewise, they ask a lot of questions. Right? So, now I am going to take the travelling microscope, again show you each and every part and take the measurements. Observe it carefully and answer the questions. Alright. So, if you see the apparatus here, this is the travelling microscope. This is the primary apparatus here we are going to use. There are lots of parts in it. I need to explain to you how we use each of these parts, how we get the measurements little by little. I will explain to you. You can see this is a rubber tube. This is a rubber tube. You can see this is a rubber tube. I'll be using this rubber tube and I'll explain you how we can find the thickness of this rubber tube wall, right? Also we have a glass tube. We have a glass tube. I'll show you how we can find the internal diameter of a glass tube, right? It is something similar to a capillary tube where the internal diameter is very small, which cannot be measured using vernier. So, here I will show you how we are going to measure the internal diameter of this capillary tube. Right. Before we go to the measurements, first let us see the different parts of this equipment or this apparatus. Travelling microscope, what are the different parts in it, what are the names of it, how we are going to use each of these parts, let us see now. Right students, so if you see the main parts of this equipment, you see you have this long part here, this is what we call telescope. This telescope you can rotate it, you can loosen this screw and you can rotate it in whichever the direction you want it, right. So, how do we fix it? First you must know there are two lenses in this telescope. There is one lens on this side which is fixed, which you can't move front or back, you can't move it, it's a fixed one. And then on the other side here we have another lens, which you can move front or back, you can move it. And this movable lens is what we call the eyepiece, the eye lens, right. And this fixed lens is what we call object lens, the objective or object lens, right. First you need to identify that. Why? Then only you know in which direction you have to keep the object. Let us say you have an object here, you want to measure something on that object, then you have to make sure the telescope is turned like this, because when the object is here, object has to be placed next to the objective, next to the object piece, and the eyepiece is here through which I can observe the object like that. What some students do, if you have not used this previously, they don't know which is objective and which is eyepiece. Sometimes they fix it like this and they try to look like this, which is incorrect, you won't be able to see anything, right, you won't be able to see clearly. So, make sure first you identify the telescope and identify the two lenses, which is eyepiece, which is object lens, you need to identify. That is one part about it. Then, before we start using this apparatus, we have to ensure this base is horizontal. Sometimes the table where we keep may not be horizontal, table might be slanted. Then the measurements you take, the vertical measurements you take might not be right. Therefore, first we have to make sure this base of this microscope is horizontal. For that only we have this spirit level here. We have this spirit level, the bubble level or spirit level. If the bubble is right in the middle, then we know it is horizontal. Sometimes it may not be in the same plane, same level as of the table, because table is not horizontal. So, don't ever compare this with the table, right. Don't ever try to keep it parallel to the table, because if table is not horizontal, then this won't be horizontal. All what you have to check is look at the bubble level. If bubble is right in the middle, then it is leveled, it is horizontal. If bubble is not in the middle, then you have to use these two screws. You can see we have two screws in either sides here. We have to use these two screws and make sure it is leveled horizontally such that the bubble level is right in the middle. Right, these two screws, you have to use these two screws for that. So, they ask this in the exam, they ask, okay, when you start the experiment, what is the first adjustment you do? First calibration you do, which screws you use for that? These two. Suppose in the travelling microscope that you have, if this bubble level or spirit level is not there, you can take a separate spirit level, you can keep it on this plane and level it, even that is possible. Clear? Right. So, that is about leveling it. Then we have a lens here, a hand lens or magnifying lens is there. Usually it comes with the travelling microscope. Why do we use this? There are vernier scales. Sometimes you may not be able to see clearly with your bare eyes which line of the vernier scale is aligned with the main scale. For that we can use this lens. That also, in case in your laboratory the travelling microscope you have, if it doesn't have a magnifying lens, you can take a separate lens. Any lab will have a usual hand lens. You can take a hand lens and use it as a magnifying lens here if you are finding it difficult to take the measurements. Actually, you should be able to get the measurements with bare eyes. That's how the vernier is. But still, if you find it difficult, you need a closer look, you can use this magnifying lens. Let me keep it aside to show the other things more clearly to you. Right. After that, you can see there is a horizontal scale that goes like 0, 1 centimeter, 2 centimeter, 3 centimeter, likewise similar to a meter ruler, it has scales on it. And each centimeter is divided into 10 sections, 10 divisions. That means each division is a millimeter. And that millimeter division is also again divided into 2. That means each fine division is 0.5 millimeter. Every small division we have here is 0.5 millimeter on the main scale. That's the same for the horizontal scale as well as vertical scale. Then we have a vernier. We have a vernier here. This vernier has 50 scales. They have marked it as 0.1, 0.2, 0.3, 0.4, 0.5. Within those 5 divisions, again there are 10 subdivisions. So 5 into 10, 50 subdivisions are there. I'll explain you in a while how to use that and how to find the least count. I'll explain. For the moment, let's just have a look at it. So there are 50 divisions and there is a vernier scale horizontally as well as vertically. So we call it a travelling microscope, right? Where does it travel? How does it travel? Why does it travel? Let me show you. Let's say I have fixed it like this, fixed the microscope like this, and let's say I have something like this of which I want to measure the thickness. Let's say I want to measure the thickness of my finger, right? Then what you do, in front of the objective, you fix your finger or the object of which you want to get the measurement. So how do I get the measurement? First I focus it on this side and get the measurement. Then I focus it on the other side and get the measurement. How do I focus? There is a crosswire inside. When I start getting the measurements, I will show you. So get the crosswire on this side, get the horizontal reading, and then you have to get the crosswire on the other side without moving the object. Keep the object fixed. You have to move this microscope. How do you move the microscope? You don't move the entire body of it. You don't take it like this and move it. No. How do you move the microscope? This microscope, this stand of the microscope can be moved on this railing. On this railing, it can move horizontally. I'll show you how it moves. Can you see there's a screw here? First thing, if you want to move it by a bigger scale, like few centimeters if you want to move, loosen this screw and then hold your microscope. Otherwise, the entire body might shake or move. Hold it tight and move this. Can you see? You can move it. That's how you change the focus from one point to another point. Now, do you understand why we call it travelling microscope? It moves. It moves. Suppose you need some fine tuning. Because when you are moving by hand, it moves by a bigger extent, right? It moves by a few centimeters. You need very minute tuning. Let's say parts of millimeter you want to move. 0.1 millimeter, 0.2 millimeter you want to move. Then how do we do it? You tighten the screw, and then you have another screw here. Rotate this screw, that will make sure your microscope moves horizontally by fine distance, like 0.01 millimeters, very slowly. You can see it here. See, when I rotate this, it moves. Now, if I rotate the other side, other direction, it moves to the other side. Understand? So, if you want to move it by a bigger distance, for example, when you measure the capillary tube, internal diameter, once you get one side's measurement, to the other side, you don't have to move much. Right? It's like 1 millimeter or something. Then, don't move by hand. Tighten this, and then move with this. And remember, if you don't tighten this, if this screw is not tightened, then when you rotate this screw, this one, fine tuning screw, you won't see a movement here. If you want to use the fine tuning screw, make sure this has to be tightened. This was even tested in an exam, in a recent final exam, advanced level exam. They asked, when a student started using this microscope, when he was rotating the screw, there was nothing happening. The microscope did not move. What could be the reason? And the funny part of it, half of the students have written the answer, microscope might have been corroded. No, that's not the reason. Usually in the labs, we don't let the apparatus get corroded. The reason is this: you did not tighten this. See, if you loosen this, and then however you rotate this, this will not move. Right. So this has to be tightened, and then you fine tune with this. A similar arrangement is there on the vertical scale also. You have a vertical scale here, and there is a vertical vernier. Vertical scale is in centimeters. Each centimeter is divided into 10. So that is 1 millimeter. Each millimeter is divided into half. That means half a millimeter. Right? And there is a vernier with 50 divisions. And if you want to move vertically, let's say you want to get the measurement something like this. If you want to get the thickness, first you have to get the measurement at this point, then the top point. So you have to move it vertically up and down. So how do you move it vertically up and down? Can you see there's a screw here? You have to loosen that screw. Careful, if you don't hold it, here we have a handle. We have a handle here. You have to hold on the handle and loosen this. Otherwise, what will happen? The moment you loosen, it will fall down. See, it falls down. Right? So don't let it fall down. Don't damage the apparatus. Make sure when you are loosening this, you hold it on this side. You have a handle here. Hold it and move it the way you want it. You can go down if you want, or you can take it up if you want, whichever the way. Right? Tighten it. You can't let it without tightening it because it falls down. Horizontal one, even if you don't tighten it, no problem. It will just stay there. Only thing, this screw wouldn't work. But vertical one, if you don't tighten this screw, this falls. Your microscope will fall down. So make sure you tighten this. And vertical fine tuning can be done by this. After you tighten this screw, vertical fine tuning can be done by this. Right? When you rotate this, it goes in one direction. When I rotate the other direction, it moves down, up and down. Fine tuning, like 0.01 millimeters, it moves up and down. Right? That's how we move it vertically and horizontally. Since the microscope can move and get the measurements vertically and horizontally, we call it a traveling microscope. Right? That's all the primary parts on it. Couple of other things I have to tell here. Make sure when you keep this apparatus, you keep the scale, where the scales are marked, you keep it to your side. Right? When you are doing the experiment, you have to keep it like this. See, suppose you keep it the other way around, you can still keep it. Say you have kept like this, still you can keep it, right? Then you have to change it. Okay, you have your eyepiece is here, objective lens is here, you keep the object here, you can zoom and everything, you can adjust everything. But to get the readings, you have to run around to the other side and get the readings. Right? See, from this side I can't read anything because the readings are here. So make sure you don't do such mistakes. It has to be kept in the right orientation. It has to be kept in the right orientation. Right? See, this is where we keep the objects. Say when we are using it vertically. Right, this is where we keep the object. So that's why this base is given to you. You keep the object here. Or you keep it like this. Fix the object in a stand or something in front of it and get the measurement. Make sure while you take the measurements, until you finish taking all the measurements, object doesn't move. Suppose after taking one reading, if you have moved the object and then if you get the second reading, then it's not precise because you have moved it. So until you finish from the first reading until the last reading, object has to remain unmoved. Understand? So those are the primary elements of this traveling microscope. First, what we need to do before even we level this, first thing, understand how to find the least count of it. Usually the least count is written. If you look at the vernier, it's written there, it says 0.01 millimeter. Right? So even if you don't calculate it instantaneously, you can use it because it's written there. But still, it is always better. We should know how to find the least count. So next, I'll show you how to find the least count of this. Students, now let's see how to find the least count of this traveling microscope. You know how we find least count is, you find the length of one smallest division in vernier scale, the length of one smallest division in main scale. The difference between those two is what you call least count. Main scale, we know smallest division is 0.5 millimeters. 0.5 millimeters. Right? Now, let's find the length of one smallest division of vernier scale. As you can see here, 49 vernier scales or 49 main scales are aligned with 50 vernier scales. 49 main scales are aligned with 50 main scales. I repeat, 49 main scale divisions are equal to 50 vernier scale divisions. 50 vernier scale divisions. When you say 49 main scale divisions, each main scale division is 0.5 millimeter. So 0.5 into 49 means that's 24.5 millimeters. So the 50 vernier scales altogether, 50 vernier divisions altogether is equal to 24.5 millimeters. So how much will be one division? 24.5 millimeter divided by 50. That is, you get 0.49 millimeter. That means each vernier division is 0.49 millimeter. Each main scale division is 0.5 millimeter. 0.49 millimeter, 0.5 millimeter, you subtract it, you get 0.01 millimeter. That is the least count. That is the minimum measurement minimum change in measurement you can get when you are using this traveling microscope. That's what we call least count, 0.01 millimeter. After identifying the least count, after you have leveled it horizontally, right, it's already the bubble is in the right middle, so I don't have to do any additional leveling activity here, it's already leveled horizontally. The next calibration you do, in the eyepiece, when you look through this eyepiece, you will be able to see a cross wire, one vertical wire and one horizontal wire. You will be able to see a cross wire, right, a sign like cross. You have to adjust this front and back, like forward and backward, you have to adjust it and make sure you see a clear image of that cross wire, right. So let's see how we are going to do it first. After you do that adjustment, then you should not touch on the eyepiece. You can continue with the rest of the measurements, right. So let's see how I am going to adjust my eyepiece and make sure I see the cross wire clearly. Right. This is the position I see the cross wire clearly. That means now the eyepiece has been calibrated. I can, the apparatus is ready. I can start taking the measurements. First measurement I am going to take. Let's take a glass tube, the one I have shown you, and I'll show you how to find the internal diameter of it. Right. So you can see I have fixed the the glass tube here. I'm going to measure the internal diameter. So, how do we measure the internal diameter? See, if you have a like through this eyepiece, first I have to see the clear image of this glass, the cross section of glass I should be able to see. And you know, cross section will look like a circle. It will look like a circle. So, how do we get the diameter? The cross wire, the horizontal line of cross wire should be adjusted such that it becomes the horizontal diameter of that circle you see. And the vertical line of the cross wire should become a tangent to the internal circle. So, you have to move this microscope, bring it to one side to be the tangent of the internal circle. Which is tangent? The vertical line of cross wire should become the tangent of the internal circle. Get the readings of the horizontal scale. And then move the microscope to the other direction and make the vertical line of the cross wire tangent on the other side of the circle, again the internal circle. So, if you have the internal circle, you will have two tangents, right? Two vertical tangents. So, at two vertical tangent positions, get the readings. The difference between those readings will give you the diameter, internal diameter of this glass tube. Usually, to improve the precision, what we do, if we get the horizontal diameter's length, then you get the vertical diameter's length also, and then get the average, so that you can get more precise answer. So, how do we get the vertical diameter? The vertical line of the cross wire should remain on the diameter itself. Horizontal line of the cross wire has to be moved up, make it the tangent to the internal circle, and then move it down, make it the tangent to the internal circle again, get the readings, both readings you get it, the difference will give you the vertical diameter. So, that is what I am going to do it now, right. At this position, I do not see the image of the cross section of this glass tube because it is too close. So, usually when we start, we keep it too close and little by little we move it backwards to find out where the precise position is. At this position, I can see, I can fine tune it with this knob. Right, at this position, I can see the clear image of cross section of this glass tube. Now, what should I do? I am going to get the horizontal diameter. Now, the vertical line is not there as the diameter. So, I am going to move it horizontally a little bit such that the vertical line becomes the diameter. And then the horizontal line is also not there as the diameter, it is a little bit up. Let me bring it down. Now, actually the cross wire is right in the middle of the circle, right. The intersection point of the cross wire is almost the center of the circle. Now, what should I do? Move it rightwards and leftwards. Make the vertical line of the cross wire as the tangent to the internal circle and get the measurements. Right. At this point, you can see the vertical line has become the tangent of the internal circle. Let me get the reading on my horizontal scale. At this position, I can see the vertical line of the crosswire has become the tangent to the internal circle of this cross section, right? So let me get the reading at this point. The zero of the vernier has passed 29 millimeters. 29 millimeters it has passed on the main scale, but it has not passed 29.5. So it's in between 29 and 29.5, it is there, right? Now I have to check the vernier scale where it matches, where it becomes collinear with another division on the main scale. The 0.4 line, that means the 40th line, they have marked it as 0.1, 0.2, 0.3, 0.4. 0.4, 40 line means 40 into 0.01 is 0.4. 0.4 millimeter, that is 40th line, is what becomes collinear with another division on the main scale. So the reading we get here is 29.4 millimeters. What should I do next? I have to move this crosswire horizontally and make that vertical line become the tangent on the other side of the internal circle and get the reading again. See, since the diameter of this glass tube is very small, I don't have to adjust it by the horizontal movement where we use this knob. No, I did not use this knob because I used the fine tuning knob. That itself was enough for me to move from one end to the other end within the circle, since the diameter is very small, right? Now let's see the reading we get here. The zero of the vernier has just passed 34 millimeters, 3.4 centimeter or 34 millimeter it has passed. And the vernier, see, I am using this lens to see the vernier more clearly. Twentieth section, that means 0.2 millimeter. That is what becomes collinear with another line on the main scale. So the reading here we get is 34.2 millimeters. 34 on the main scale, 0.2 on the vernier scale, we get 34.2 millimeter. So look at the two readings we got horizontally. One was 34.2, one was 29.4. So the difference between two readings, 34.2 and 29.4, we get 4.8 millimeter is the diameter. This is the horizontal diameter that I have measured. Let's measure the vertical diameter. If it is a proper circle, it has to be same. But to improve the precision, now let's do the vertical diameter. Let's find that as well. Suppose if it is different from the horizontal diameter, then we can get the average. But if it is same, it's fine. That must be the case. So now what should I do? Let me bring now the crosswire is in one side, right? Bring the crosswire to the middle. Vertical line should be the diameter. Horizontal line of the crosswire, I'm going to move up and down. Once we will get the reading up, once we will get the reading down and get the difference. You have to understand one thing here. What we see through the eyepiece is an inverted image of the object, right? So when in the eyepiece, when I see right side of the image, actually what I see is the left side of the object. Right, what I see as the right side of the image, when I say look at the image, align the line with the right side, what actually we are doing is aligning with the object's left side. Then I would say, okay, on the image, move from right to left. When the crosswire moves from right to left of the image, actually the microscope will be moving to the other direction, because inverted image, if the image moves right to left, right, object moves left to right. Understand? Similarly, when I say, okay, let's take the reading of the upper line, let's say the circle upper tangent and lower tangent, right, the bottom tangent. When I say upper tangent on the image, that is actually the lower tangent of the object that we are measuring, because we have an inverted image. Right, be clear on that. Right. So now let's see what is the reading we are getting for the upper tangent that I see on the image. Now the vertical line has become the diameter. Let's move vertically. I don't have to use the knob here, because I'm going to just move it by small amount. I can use this fine tuning knob. Right. Now the horizontal line of the crosswire has become the tangent on the top of the image that I see. The internal circle I see, the top tangent, I have aligned it there. So when I say top tangent, actually it's the bottom tangent of the object. Be clear on that. The reading we get for that, the zero of the vernier has passed 86.5 mark. 86.5 millimeter it has crossed. So the answer has to be, the final reading has to be in between 86.5 and 87. So it can be 86.6, 86.7, 86.8. In that range, we are going to get an answer. Let's see which line of the vernier becomes collinear. The 25th division of the vernier, that becomes collinear. So 25th means actually 0.25 millimeter. So 86.5 and another 0.25, that is 86.75 millimeters, right, 86.75 millimeter. In the circle that I see as the image here, I have taken the top one. So when I say top one, for the object it is the bottom one. In the image now, what am I going to do? From top to bottom when I move, you can see the microscope will move up. In the image when it is coming down, actually on the object it moves from bottom to top. So the microscope has to go up, you can see when I get the second reading. With the fine tuning knob itself, I was able to bring the crosswire down such that the horizontal line has become the tangent to the internal circle. But when I say crosswire has come down, actually the microscope has gone up, because now we have gone to the upper circle of the object, upper line of the object. Let's get the reading now. The zero of the vernier has just passed 91.5, just passed 91.5. It has not gone to 92. Check the vernier. The fifth division of the vernier is aligned with another division on the main scale. Fifth division means that's 0.05. Already we are at 91.5. So 91.5, another 0.05, 91.55. So one reading we get 91.55. The other reading we got 86.75. If you get the difference, that gives you 4.80 millimeters. The vertical diameter becomes 4.80 millimeters. Horizontal diameter was also 4.80 millimeters. Therefore, the average will remain the same, 4.80 millimeter. Right? So are you clear how we get the measurements to find internal diameter of a tube using traveling microscope? Usually we don't take only one diameter, For the same object, you take 2 or 3 different positions, you get the diameter. So here we can move it vertically and horizontally. Therefore, you get the vertical diameter, horizontal diameter, get the average, you get a precise answer. Right. So why did I use this glass tube here? Because you can't use the vernier caliper to find the internal diameter of a glass tube because it's too small. The jaws will not go inside this glass tube. Similarly, another problem I told you with vernier, rubber tubes you can't measure the diameters because they get deformed. So you can't use the jaws of vernier to measure the diameters of rubber tubes, which can get deformed. So now I will show you how to find the diameter, the thickness of a rubber tube using the travelling microscope. Right, you can see now I have fixed the rubber tube in front of this, the microscope. Let me find the clear image of it. Right, that's the point where I get the clear image of the cross section. As we did earlier, this time what I want is the thickness. So what we have to measure is external diameter, internal diameter, the difference. Internal diameter, how to measure, I have already shown you in the previous experiment with the glass tube. So now let's see how to get the external diameter, right? First, let me align the vertical line of the crosswire to be the tangent of the external circle that I see here. Right. This is the position where I have the vertical line as external diameter, the tangent of the external diameter, vertical line as the tangent. Let's get the reading. The zero of vernier has just passed 38 millimeters on the main scale, and the vernier twenty-fifth section is aligned or is collinear with another division. So the reading has to be 38.25 millimeter. This is when the vertical line of the crossfire has become the tangent of the external circle. Now I can move it and bring it as a tangent on the other side as well, on my right side as well, right? Let's move it and see. Since the diameter is bigger, I will have to move it with the other knob here because the fine tuning knob will not be enough. Now I have brought the vertical line of the crossfire as the tangent on the other side of the external circle. Let's get the reading now. Zero of the vernier has passed 26.5 millimeter. 26.5 millimeter on the main scale it has passed. Check the vernier scale. The 35th line is aligned with main scale. So 35th line means 0.35 millimeter. We are already at 26.5 on the main scale. 26.5 and 0.35, 26.85 millimeter, we get the reading here, right? So now the reading I have got already, and this reading 26.85, if we get the difference between these two, that will give you the horizontal external diameter you get. Horizontal external diameter you get. Similarly, if I can get the horizontal internal diameter also, then if I get the difference between internal diameter and external diameter, that will give me twice the thickness of this rubber tube. Twice the thickness of this rubber. Why twice the thickness? External diameter, internal diameter, both sides the thickness is covered, right? So twice the thickness you get, right? I have done it horizontally. Let's do it vertically as well. Bring the crosswire to the middle and let's move it up and down. Now I have taken the horizontal line of the crosswire to be the tangent on the upper side of the image I see. When I say upper side of the image, actually lower side of the object, right? Upper side of the image, it has become the tangent. Let's get the reading. I have to get the reading on the vertical scale. The 0 has passed 94 millimeter on the main scale. It has just passed 94 millimeter on the main scale. Let's see the vernier scale. The 10th line of the vernier scale is aligned with the main scale division. That means 0.1 millimeter. So the reading is 94.1 millimeter. Now what should I do? I have to bring down the crosswire and make sure on the image it is aligned with the bottom. That means the horizontal line has to become the tangent on the bottom side of the image. Yes. On the image I have brought it down. On the image if I am bringing it down, actually the microscope has gone up. Because on the image I am going to the bottom line means to the object it must be the upper line, right? So the microscope has gone up. So I should get a reading which is bigger than 94. Even though I say I have brought down the crosswire to the bottom of the image, to the object it has gone up. Right. So when the microscope moves up, I can see the crosswire moves down on the image because we have an inverted image here, upside down image here. Right. Let's get the reading now. The 0 has passed 105. 105 it has passed. That is 105 millimeters. Check the vernier. 40th line of the vernier is aligned with another division on the main scale. 40th line means 0.4. So the reading is 105 on the main scale, 0.4 on the vernier, 105.4 millimeter we get the vernier reading now. So the difference between the previous reading we got 94.1 and this 105.4, if you get the difference between those two, that will give you the vertical external diameter. I am interested in finding the thickness. So what you have to do next? You have to find the vertical internal diameter also. How to find the internal diameter? I have already shown with the glass tube. So using that technique, find the internal diameter also, get the difference. Again, that will give you twice the thickness on the vertical side of it. So which way you can find the thickness horizontally, vertically, get the average value of the thickness as the overall thickness of this glass, of this rubber tube. Right? When we do the experiment in heat, in a section called heat, we have something called finding the heat conductivity of a rubber tube. There the thickness will be required, right? So at that point we have to use this traveling microscope and find the thickness. This is how we find the thickness. Are you clear? So now do you understand how we use the travelling microscope to find the internal diameter of thin tubes like capillary tubes and find the thickness of rubber tubes. So, we have done all the measuring equipments with this, the vernier caliper, micrometer screw gauge, spherometer and travelling microscope. I have done it for you. Practice all this, right, whatever the questions you come. This is kind of a bit more detailed one, right. They ask you about each and every part here. So, make sure you learn everything and you are clear about it. Okay. Next we will see, we will meet up with another experiment in the section mechanics. Students, now let us see a past paper question that has come about this experiment. 2018 past paper, actually that is a mix. They are asking about travelling microscope few questions, and the latter part of that question is connected to an experiment in the geometric optics, right, in the section light, finding the refractive index of a glass block. So, if you have not studied that part yet, the particular questions on that you can come back and revisit later, right. Anyway, I will do everything now, I will try to explain it to you. Listen, you are asked to find the refractive index of glass using a rectangular block of glass and a travelling microscope. A small amount of lycopodium powder and a piece of white paper cut to the size of the glass block are also provided. A letter X is marked in the middle of the white paper. Diagram of a travelling microscope that can be used in this experiment is shown in figure 1. Right. So, we all know travelling microscope, that is what we have seen now. Part A. Identify the parts marked with A, B, C and D and briefly state their functions. Right. Let us look at the parts A. See, this knob is what they have marked A. I will write it clearly for you. This knob is what they have marked B and where C. These two knobs they have marked as C, and here the spirit bubble they have marked this as D. So, what is the purpose of this A? To move this microscope vertically by smaller distance. That means fine tuning the vertical adjustment of this microscope, right. We call it fine adjustment knob, vertical. What is B? B is the focusing knob. Using B only you focus on the object. Yes. See, what are these two? Those are the leveling screws. If it is not horizontal, right, if the base of this travelling microscope is not horizontal, you can use these two screws to make it horizontal. D is the bubble level or spirit level. You use that to verify whether the base is horizontal or not. Let us write it A, fine adjustment knob, fine adjustment knob. What do we do with that? Vertically adjust the vertical position of microscope by smaller distance. B, what's B? B is this focusing knob. What do we do with focusing knob? To focus the microscope on the object and get a clear image. C, See are the leveling screws. Leveling screws. What do we do that for? To level the base of the microscope horizontally. To level the base of the microscope horizontally. D is the bubble level or spirit level. We'll say spirit level. What do we do with that? To verify whether the base is horizontal or horizontally leveled, right? That's what you call spirit level. We know that when we did the experiment, we have looked at each and every part. Simply they are asking you to explain that. Before starting the experiment, while familiarizing with the travelling microscope, a student observed that when the fine adjustment knob relevant to the horizontal movement was turned, the corresponding vernier scale did not move. Give the reason for this. Look, now this is the particular knob that they are talking about. This is a horizontal fine adjustment knob. When you move that or when you rotate that, this microscope has to move horizontally on the base. On the trailing, it will be moving by minute distance, by small distance, fine adjustment knob. So, why isn't it moving? You remember I told you we have another knob here, this one. That is the horizontally adjustment knob, not the fine adjustment knob. Now, what do? We loosen it, then move it by larger distance, by few centimeters. If you want to use the microscope, we use that. And then you have to tighten that knob. If you tighten that only, then the fine adjustment knob will work. If you forget to tighten this knob they have named it as F. If knob F has not been tightened, that means the horizontal adjustment knob is not tightened, then the horizontal fine adjustment knob will not work. I have shown that. You have to write that. Unfortunately, half of the students who have written this paper, they wrote maybe because the equipment is corroded. Maybe it's malfunctioning. No. Corrosion, malfunctioning, all that we don't allow it to happen on the lab apparatus. So, you can't take those answers as granted, right? That never happens. We won't allow that, right? You have to give a proper feasible reason. That cannot happen with the vertical adjustment. See, vertical also, look at this H. H is the knob, we use it to vertically adjust it by larger distance. So, after adjusting it by larger distance, you can't leave it loosened because then microscope will fall down. So, nobody will leave it loosened, they will tighten it for sure. After tightening that only, knob A will work. So, vertically, since you can't leave it loosened, this mistake doesn't happen. But horizontally, you loosen it, move it, and then you can leave it there, right? It doesn't fall anywhere. So, people might forget to tighten the screw again. Then the fine adjustment wouldn't work. So, let's write, because knob F, horizontal movement was turned, the corresponding vernier scale did not move. Give the reasons for this. Knob F is not tightened. Next, an enlarged figure of the main scale and the vernier scale of a travelling microscope are down. Calculate the least count of this travelling microscope in centimeters. Least count, let's see, look at the main scale. This is the main scale. This is 1 centimeter, that is divided into 10. So, each small division is 1 millimeter, and that also again divided into half. So, each small distance in the main scale is 0.5 millimeter. Each small distance in the main scale is 0.5 millimeter. 1 centimeter, that is into 10, and each of those 10 sections is again divided into 2, half. So, 1 millimeter into half. Now, the vernier scales division, let me check. Look at this, 1 centimeter, 2 centimeter, 21 millimeter, 22, 23, 24, 25 millimeters. Am I right? Not 25. Let me check again. 20, 21, 22, 23, 24, 24 and a half. 24 and a half millimeters are given by 50 divisions in the vernier scales. 50 divisions of vernier scale is actually 24.5 millimeters. How do I know? 2 centimeter, and then there is another 4.5 millimeter. So, 24.5 millimeter on the vernier, on the main scale is equal to 50 divisions in the vernier scale. So, you know the least counts means the smallest distance or smallest division of main scale minus smallest division of vernier scale. So, smallest division on main scale we have got it as 0.5. Smallest division on the vernier scale we have to divide like this and find it. So, if you take 50 as the common base, it is going to be 25. You get 0.5 over 50. This is in millimeters. So, that is 0.01 millimeter. 0.01 millimeter is what you get. Right? What is the adjustment that you perform on the eyepiece before starting the experiment? Before starting the experiment, at the beginning, what do? You adjust the lens of the eyepiece until you see a clear image of the crosswire. You have to do that, right? So, let us write it. Adjust the eyepiece to get or to see a clear image of crosswire. That is what we do first on the eyepiece. Now, you are asked to place the given piece of paper on stage G of the travelling microscope and obtain the first measurement with the microscope using mark X before placing the glass block. Write down the main steps in the experimental procedure you would follow to achieve this. Now, let me explain a little bit of geometric optics, because from this part onwards, this is also microscope, fine, but after this the next two parts are about the geometric optics. You know, there is something called refractive index of materials. That means the materials through which light can penetrate. For example, light can come through space, light can penetrate water, light can penetrate glass, light can penetrate diamond. So, when light penetrates through different materials, the speed changes, right? The speed changes. Light does not travel at the same speed in all the media. Medium to medium, the speed will be different. Then, to reflect that speed difference, we have something called refractive index. That index is something connected to the speed of light in that material. So, refractive index of water. That means refractive index of light in the medium water. For glass, we have a refractive index. For diamond, we have a refractive index. And this refractive index, there are several methods of finding it. One good method is this. Listen. Say, now, let us say this is the glass block. Let us say this is the glass block. Let us say you have put a small mark here, something is there. Let us say a small insect is there, okay, an ant which has been caught under the glass block. Now, when you look at this ant from here, that means from above the glass block, when you look through the glass block, how the ant will look like? Ant will look like it is somewhere here, right? So, this is the real position of ant. Since you look it through the glass block, you will see it displaced a little bit upwards, right? If you haven't seen this phenomena, check that. You take a glass block and see, you will see things are a little displaced upwards. So, there will be a displacement, right? Now, this distance, which distance? Look at this. This distance is what we call real depth. Real depth, right? This is what we call apparent depth, because this is where actually the particle is, but when you look from here, it looks elevated a little bit. So, it looks elevated, that is why you call apparent depth, right. The refractive index of this glass block is defined by n equals real depth divided by apparent depth. Real depth divided by apparent depth. Apparent depth. This will give you the refractive index. This is some theory that we study in light. That means there is a section called light. Geometric optics is the correct name of it. Within that we study this. But how do we get these measurements? We are going to use the travelling microscope, right. You need to get 3 readings for this. 3 readings. How do you get 3 readings? Look at this. Reading number 1, without the glass block, just keep a paper, mark it as X and focus on X and get the reading. So, basically you are getting the reading at this point. Reading number 1. Without the glass block. Then on top of that paper, keep the glass block and get the reading. Keep the glass block and get the reading means keep the glass block and again focus on the cross. On the paper you have written a cross, right? Earlier you focused on that. Now you keep the glass block, it won't be focused now because the cross will look elevated. So, previous position of focusing the microscope wouldn't give you a clear image now. So, you have to readjust it and get another image or another position of microscope, get that reading. That's going to be the reading at this point. Reading number 2. On the vertical scale, this is going to be the reading 1, this is going to be the reading 2. Then what you do, on top of this glass block, you put some powder. There is this yellow color powder known as lycopodium powder, right? Something almost similar like turmeric. It will look like turmeric, but it doesn't dissolve in water. It's a wooden powder, right? It doesn't dissolve in it, it floats. Even in water, it floats, right? So, turmeric might get dissolved in water, right? But lycopodium powder, it just floats in water also because it's wooden powder. So, put some of those powders on the top. Now, focus your microscope on this powder and get the reading. That's going to be reading number 3. So, real depth means the difference between reading 3 and reading 1, right? Reading 3, reading 1. Apparent depth means it has to be the reading difference between reading 3 and reading 2. Understand? So, using travelling microscope, we just have to get these 3 readings and apply in the formula, you will get refractive index of glass. So, that is a little bit from geometric optics I explained to you. But now you understand what is relevant for us in travelling microscope is how to get these readings. Simply how to get these readings. So, they are asking, write down the main steps in the experiment procedure you would follow to achieve this, not for the whole experiment, to get this first reading, reading number 1. They say they have already kept the paper where the cross is written. So, now let us say, focus the microscope on the cross mark in the paper. Let's see which knobs we can use for this. Now vertically you're going to adjust it and focus it, right? Focus it. We can use where? There are multiple knobs available for you. You can use H, because if you want to move it by a larger distance like few centimeters up or down, then you need H. So knob H is useful. Knob A is useful to get fine tuning of it. And knob B is also for focusing. Focusing means basically you move the lens, right? That's what focusing. So either you can use A or B. A and B does the same activity. The difference is when you are vertically doing it, when you are just using the knob B, the lens moves within this tube, so that scale doesn't move. Let's say the lens moved by 2 millimeters up when you rotated this knob. That 2 millimeter movement will not be reflected in the scale, because that movement happens within the tube, right? Whereas same 2 millimeter you can move by knob A as well. When you move it by knob A, that will move on the scale as well, because the whole microscope is going to move on the railing, right? So clearly understand, when we get the first reading, you can use knob A or knob B, doesn't matter. But when you get the second reading, from first reading to second reading, how much it has moved, we have to measure, right? So every movement on focusing has to be reflected on the scale, right? Because with relevant to reading 1 only, you are getting the reading 2. Then after getting the first reading, when you get second reading and third reading, you should not touch this knob. You should not touch this knob. You understand? Because if you move that knob, then within the tube the lens is going to move, so that it will not be reflected on the scale. Therefore, make sure first reading when you are taking, you can adjust any knob. But when you take the second reading, third reading, you should not touch the focusing knob. You can do the vertical adjustments only with H and A. Only with H and A. Right? So let's write that here. Focus the microscope on X mark on the paper using knobs H, A and B. You can use all those 3, right? And then what do they ask? Now you can ask to place first measure E of the travelling microscope and obtain the first measurement with the microscope using mark X before place. Write down the main steps in experimental procedure you would follow to achieve this. Okay. Then let's say read the, or let's say obtain the reading. Obtain the reading. On the vertical scale. That's all. Next. Relevant position of the main scale of vernier scale corresponding to the measurement mentioned in E above are shown below. Write down the reading corresponding to the measurement in centimeters. Right. So, reading. First look at where the vernier's 0 is. 4.1, 2, 3, 4, 5, 6. 4.65 centimeters it has passed. 4.65 centimeters. Plus. Then you need to see where the vernier's division and the main scale divisions get collinear. They have given a enlarged image of that. Let's check here. Look at this line. That line is collinear with another line. All others, there is a small mismatch. But this one perfectly matches with another line. So, let's say that is 40, 41, 42. 42nd division of vernier scale. You have to multiply that by least count. Least count we have already written. Where was that? 0.01 millimeter. Careful, millimeter. 0.01 millimeter. This is in centimeters. So, let us say 0.001 centimeter. I divide by another 10 to write it in centimeters. So, you get 4.65 plus 0.042, that is 4.92 centimeters. You cannot give it in millimeters because they said give the measurement in centimeters. Or if you calculate in millimeters, then again divide that by 10, give it in centimeters. Yeah. Next. After taking the first measurement mentioned in E above, write down the important steps in the experimental procedures pertaining to the other two measurements that you need to perform. I already explained you the other two measurements. Now, you have taken this one, right? To get reading 2, what should you do? On the paper, you keep the glass block. Again, focus, again adjust the microscope vertically. Get a clear image of this cross and get the reading on the vertical scale. That will be reading number 2. And then on top of the glass block, you can put some lycopodium powders. They have given in the instruments that they are using lycopodium powder. So, you can put some lycopodium powder on top of that glass block. Again, focus the microscope, not using the focusing knob, using the vertical adjustment and fine adjustment knobs. You can adjust it and get the clear image of lycopodium powders. Get the vertical scale reading. That will be reading number 3. Let us write that. Place the glass block on the paper. Adjust the microscope vertically using knobs H and A. H and A, according to the image, it is H and A. H is the large movement vertically large movement knob. A is the fine tuning knob, fine adjustment knob, using knobs H and A to get a clear image of cross mark. Obtain the reading on vertical scale. Right, this is for reading number 2. Reading number 3, how do we get? Spread a thin layer of lycopodium powder on the glass block, on the top surface of the glass block. Using knobs H and A, adjust the microscope vertically. I am not using the term focus because when you say focus, you might mistake that you are going to use the focusing knob. That is why I say adjust it. Basically moving it, H and A, adjust the microscope vertically to obtain a clear image of lycopodium powder. Obtain reading from vertical scale. Right. Those are the main experimental procedures in getting the next 2 readings. Readings of the relevant 3 measurements obtained by another student when performing this experiment are given below. Using the Using these measurements, calculate the refractive index. So, you know refractive index, as I mentioned, reading 3 minus reading 1 will give you the real depth over apparent depth. This is real depth. Right. 7.206 minus 4.606 divided by 7.206, 5.496. That is 3.6. No, not 2.6 divided by 0, 10, 9, 1, 11, 1.7. 260 divided by 171. 1, 89, 5, then you have 35, 352. 1.52 is the answer that you get for refractive index. So, only the last part or last one and the previous one are connected to geometric optics. Apart from that, all other parts, see, all other parts, maybe this one you need to know a little bit of geometric optics. All others before that are on the usage of travelling microscope. Clear? So, don't ignore these measuring apparatus practicals, because they also can be tested as one full structure question. Even if they don't test it as one full structure question, with some other practicals, this can be mixed together to give you a structure question. Right, focus on that. I have done mainly 4 experiments on the measuring equipments. First one was on the vernier caliper, second one was on the micrometer, screw gauge, then spherometer and travelling microscope. Right, practice all these 4 very well, do all the past paper questions that I have done, use that, do that yourself and see whether you are really okay. Now, let us move on to another experiment.